machine learning, and mostly in applications to real-world problems. So I've worked in various different applications, including health and medical imaging, and autonomous driving, sports analytics, and also some preliminary work in natural disaster monitoring. The core theme of most of my research is around developing robust and trustworthy artificial intelligence, or AI, systems. So specifically, that's around understanding the developed models and interpreting them, so giving that human understanding. In addition, a technique called uncertainty quantification or uncertainty estimation, so knowing how confident a model is in its predictions, which can help in giving trustworthiness to models. And another technique called domain adaptation, where you can train a model in one domain and then adapt it to a new domain. Another theme of my research is around developing computationally efficient models. This is another very important aspect of deployability, because typically when we train models, we train them on massive computation. And that's not always available when you deploy these models in the field or in hospitals. So another aspect I look at is model compression and mostly a technique called knowledge distillation. So I'd like to start by motivating this talk and some of the history with AI competing against doctors. Looking at the figure on the right, you can see the y-axis is a timeline from May 2016 through to November 2017. On the left in red, we have when AI wins, and you see on the right is when doctors win. And various different applications ranging from surgery through to Alzheimer's, general diagnosis, and all the way up here to pneumonia. So this is a little bit of an old graphic, but what you can see is this trend towards AI-based models starting to actually exceed the performance of human experts. In fact, in a recent paper, this was a presentation I attended last week, a dermatologist has shown this is computers' performance here, and this is the difference between humans of different experience, so from less than 1 year all the way to 10 years of experience, how their performance compares to AI-based models in dermatology, so classifying skin lesions based off images. So is it cancerous, is it non-cancerous? And what you can see is that even though experts are obviously better than people who are less experienced, in all cases, AI is currently beating experts. Now, one important thing in healthcare is there is that potential for AI to actually improve things such as detection, diagnosis, treatment, and monitoring. However, a major limitation that's prevented the widespread adoption of AI, and particularly deep learning models, which are the state of the art at the moment, is their black box nature. So what do I mean by that? Here I have a black box. So you feed in some input, for example, a chest X-ray, and the deep learning model will produce some output. In this case, it's trying to diagnose various chest diseases. In this case, it's diagnosed that as pneumonia. So based off that, people can perform various treatment on people. However, I think you or I would not be satisfied just trusting that based off just the model outputting that. Really what you need to be able to trust this and utilize it in practice is some form of evidence or reasoning behind the classification. So opening up that black box to understand evidence, some explainability behind how it produced that classification, as well as perhaps some kind of certainty or indication of how certain the model is of its classification. So here's an example of a model for predicting the following three classes: normal X-rays, ones with pneumonia, and ones with COVID-19. This was during the height of the COVID pandemic. And what you can see is that this particular model was state of the art. It was performing exceptionally well. And if you look just solely at the accuracy metrics, you can see that you get excellent performance. This is 93% accuracy. It's only making errors very, very rarely. However, if you actually look at the evidence or explainability behind the classification, so investigating this model and delving into that black box, what you can see is that in certain cases, it's actually using incorrect information to make its predictions. What you can see here is these are 3 example chest x-rays, and the red parts correspond to what the model thought was important for classification. So in this case, you can see that there's a red on this label that says portable. So what that means is that the machine learning model is learning to associate that people who have had an x-ray taken on a portable scanner are more likely to be unwell. That is a correct correlation, because if you're too unwell to move, they tend to use a portable scanner. However, that does not mean that you have a disease. A healthy person can also have a scan on a portable scanner. Other cases might focus solely on the text labels, or in some cases might not even be looking at the lungs at all. So you can see here, it's looking outside of the lungs. So we can see that explainability is very important for actually delving beyond just the accuracy metrics. So there is a field that exists for investigating machine learning models and deep learning models called explainable AI, or XAI for short. And what that is techniques and methods that make a model's decisions understandable by people. In addition, beyond the model, there's also a need to understand the data. Here we have 2 examples of explainable AI techniques. On the left, you can see a technique called feature visualization. So that's looking at what features a neural network model learns. So it tries to figure out what it's looking for by generating examples. So here you can see it's looking at some form of texture. It's a little bit uninterpretable, perhaps, but you can see that that's what that particular neuron in the neural network is looking for. On the right, we have something called feature attribution, which is figuring out which parts of an input example are responsible for the network behaving in a certain way. So here we can see that the red parts correspond to those that trigger dog, and the green parts trigger cat. And so it looks like the model's doing a good job, because that is fairly interpretable. So as I hinted at before, a big challenge of applying deep learning models is that we can't really accept the model's outputs without any evidence of the decision-making process. And if we do, we are prone to making errors. And so there are some potential solutions to this. So beyond just accepting the output classifications of a model, we can actually investigate the distributions as well as the source of the data itself. We can provide evidence and explainability. We can quantify how certain or uncertain a prediction is. And we can also do techniques to help combat some of the underlying issues through domain adaptation. So here I have an example. Before you even do any kind of modeling, you can actually look at the raw pixel values if you're studying images. So this is, again, the chest X-ray data set, which has the 3 classes: normal, pneumonia, and COVID, indicated in blue, white, and red. And this is just the distribution of the pixel values. The way that this is acquired is you have an image, let's say it's 256 by 256. You basically just get that as a vector, and you can project that down into 2 dimensions. The spacing between these points relate to how similar those pixels are to one another. So if one point is close to another, you'd expect that the image should be fairly similar. So I'm just going to jump to the interactive version of this plot. So here we can see that we can mouse around and look at those chest X-rays, and hopefully you can agree that as I'm mousing across these images, they are fairly similar for the points that are close to one another, and as you get further away, they get different. So this is literally just looking at the pixels. So already we can see some interesting facts about the data, so how spaced out they are. We can see that we have some very white images, some very dark images, so there's some differences in the scanners that we use to acquire these images, and these are colored by the classification. So just based off raw pixels, you could almost perform classification. One problem, though, you can see if we look at changing the color of the pixels to instead be based off the source of the data. So I believe there's 6 databases that were composed to make this one database, that they're actually very much clustered. So these ones which are all very white, they come from one scanner, so one data set. These ones are from another one, but they're, I guess, separated a little bit. But you can see that perhaps there's going to be some confounding issues in the scanner that was used to acquire this database. So here you can jump between the two, and we can see that there is this correlation between the source of the data and the diagnosis label. So already we can see that there's going to be perhaps a source of error in our modeling, where perhaps it might model the source instead of the actual target disease. So in terms of some of the explainability techniques, feature visualization is where we're actually looking at what the neurons are what the neurons trigger on. So we saw these examples before of a neuron, and this is a channel. So this is at different abstractions of a neural network. We can also perform this at a layer level, at a class logit level, and a class probability level. So that's on the input to a softmax layer on a neural net, and this is on the output. Apologies if that's unfamiliar, but basically what we're looking at is that there's different levels of abstraction. This Deep Dream one, did anyone remember when that came out a few years ago, Deep Dream? Yep. So that's basically where it was like hallucinating these like dog snouts on images. So you can see that's at a layer. But we can also do it at a class level, which can provide us class information. The way these are done is through a technique or a library called Lucid, which reverses the optimization process. So it maximizes an image rather than getting the prediction. So one technique that we can utilize for understanding neural networks is called semantic dictionaries, which was proposed by Chris Olah and others in this Distill article. And it combines the what features on the previous slide with the where. So as an example, we can see here that if we mouse over this particular region, so that's the dog's nose, this is the activation vector. That's actually super interpretable. I think to me that looks like a dog snout. And then we can see the contributions of the different features. So you see it's some kind of fox-like feature here with some kind of, I don't know, also kind of snouty nose features. And we can see how much they contribute to that prediction. So if we apply this to try to understand the COVID-net model, and so that's for chest x-rays, turns out all the features that come out are nearly the same. So this is a distribution of the channels, so they're numbered by where they appear in the neural network. And we can see this is the magnitude of those channels. So this one here is 1596. That's this feature visualization here. And we have 1329 here, which is this one here. And so what we can see is that the neural network, irrespective of the class, the distributions are the same for each of the 3 classes. It's basically just looking for rib-like features. And so we're not really getting any kind of intuition behind what the neural network is looking for specific classes. Basically, it's looking for ribs regardless of what disease it's looking for. So unfortunately, if that were the case, we would all be unhealthy by having ribs. So that is actually obviously not very explainable or very useful. So what we can do is instead update this model to return class-specific features. So for those 3 classes, rather than just looking at what the neural network's looking at, we can look at what it's looking at for a particular class, for example, pneumonia. So here we can see that for this particular grid, these are the feature visualizations and their contributions. And this is specifically for the class of pneumonia. We can kind of see that it's looking for maybe patchy images. That could make sense because pneumonia presents as kind of this fuzziness in the lungs, which indicates inflammation. Then for COVID, there's these types of visualizations which perhaps at the early stages, they were saying that might indicate things like occlusions, which is slightly different from what would present in pneumonia. And so looking at that, there's this explainability tool that we developed for studying chest x-rays, where you can look at what the neural network looks for normally and what it looks for each class. And so we can see that maybe it provides a little bit more intuition behind what the neural net's looking for. And then we can see that as part of the user interface. This is just a video from the UI. And so it makes the model's decisions a little bit more understandable by providing the evidence of what the neural network is looking for, as well as where the neural network is triggering. So the good news is that it is here triggering on the lungs. So compared to those other examples, which it wasn't looking at the correct regions, it looks like it's looking at the right things. And we can kind of see a little bit about what those important features are. So maybe some of that fuzziness. And so hopefully these types of technologies can help practitioners to provide faster and more accurate diagnosis. But I think you probably agree that this top row, so the type of features that it's coming up with, aren't really very interpretable. They're all kind of just textures. Maybe they'd make a nice background on your computer or your phone, but they're not really helping in diagnosis, really. If we compare that to the original semantic dictionaries trained on ImageNet, which is a natural image dataset, we can see that they were so much more interpretable. Like we could see snouts, we could see faces, and so that seems to be more interpretable. But interestingly, by applying that class-specific technique to natural images, comparing to the raw activations, this class-specific score, we can see provides a little bit more about the class-specific information. So in this case, this here is a tiger cat, and the way that presents is with the stripes. And so we can see that the top feature visualization actually is stripes, which is perhaps a little bit more interpretable than these, which to me don't make as much intuitive sense. So now, can we provide some meaning to those learnt features? So here we're again looking at, this is, I think, ImageNet. So this is not the chest x-rays, but more natural images. And we can see some common channels and their feature visualizations. Before I show you the answers, can anyone guess what these are representing? So these are various channels in a neural network. So that one, coral, that's a good guess. Vegetables, yeah, both of those are really good. Which one? An iris. At the bottom, yeah, brain. So I'll show you now. So what we can do is we can actually look at the highly activating examples that correspond to that channel. So looking at the data set that it was trained on, we can actually highlight those features. Sorry, it's a bad color map, but you can see in this case, yes, very close and correct as well, so vegetables. So this is kind of detecting that texture of cauliflower. That's the meaning that we can give to this channel based off what we can see coming out from these highly activating examples. And the second one, you got it, waffles. So that's like a waffle-like texture. So you can see those little grids. And for this last one, I think someone said eyes. So we can see here that this feature visualization, so this channel seems to be triggering on feline eyes. So we can provide meaning behind the features that a neural network is learning by looking at these highly activating examples or these prototype examples. So now doing the same thing on the chest x-ray dataset, here again we can see those feature visualizations, but perhaps they are not very interpretable. To me they just look like nice textures. But if we look at the highly activating examples, we can see some commonality in what is actually being triggered, what is triggering that channel. So here, what we can see is there's a lot of these wired devices. In this one here, so this row here, it's a little bit hard to see, but you can see these things are being highlighted here. They're these text labels that are on the image. And the last one, this again might be a little bit hard to see, but looking at the commonality between these images and what it's actually highlighting is these devices here. So these are things like large medical devices or pacemakers. So that's kind of an interpretation based off the highly activating examples. So providing that human language to the machine language. So wired medical devices, text and labels, and large medical devices like pacemakers. So unfortunately, in this case, what these things are triggering on are actually spurious correlations. So, wired medical devices doesn't mean someone has pneumonia. It means that someone's being treated for pneumonia or breathing difficulties. Text labels, they are made after the fact. They shouldn't be used as part of a classification. And large medical devices, they might correspond with a patient's condition, so they might have heart problems if they have a medical device, but that should not constitute any future diseases. So it's very difficult to actually disambiguate between these, these features that it's learning. They're not actually what it should be learning. So why do these problems occur? So we could actually see a hint of it just by looking at the pixel distribution and the source of the data alone. So there's this term which is coined by this paper here, so Roberts et al., called Frankenstein data. So that's where a data set is cobbled together from other, usually public data sets that overlap. And so that introduces data duplication and biases. So this is exactly what happened in the COVID-X data set, which was used to train that model. So here in the middle, you can see the COVID-X data set, which is the one that this model was trained on. And you can see all the sources that were used to compose that COVID-X data set. So Chung 1, Chung 2, RSNA, Cohen. Now we've got some problems here. So we can see that this SIRM was used to compose Cohen, and it was also used to compose Chowdhury, but Cohen was also used to compose Chowdhury, and then this appears here. So basically, there is this data duplication that's happening. In addition, the problem is, if you have data duplication, it will actually appear those same data points in both the training set and the testing set. So if you think about that, that's going to have implications for the results. So what you're evaluating is actually going to be wrong. In most cases, the performance will actually be inflated because you're actually seeing the examples that should never be seen when you're performing your metrics. So that also introduces biases. So if you look at this Mooney data set, that was composed of children aged 1 to 5, and that was with no COVID. And that provides perhaps an explanation for why some of those chest x-rays were looking outside of the lung region. It might have learned to associate healthy scans as being children, ones that are skinnier than adults. So we can do a similar technique to before, where we can look at the distribution of the data, but now looking at that from what the features the model has learned. So when you train a neural network, if you look at one of the later layers, it will be on the order of 1,000 dimensions or 2,000 dimensions. You can then project that into 2 dimensions to see the relationship between data points and their feature representations. Again, close points mean they have similar feature representations. Further away points mean they have dissimilar feature representations. If we look at the ground truth data, so this is the ground truth labels and the source where it came from, we can see that the normal scans came from these 2 different data sets. So when it's learning what normal is, it's basically just learning where that scan came from. So that is a bit of a problem. So we can use these explainability techniques to identify these problems. We can also use other techniques such as estimating the model uncertainty to give a bit of an indication and further insight into the model's performance and its confidence in its predictions. So in terms of modeling uncertainty, there are 2 main types of uncertainty. So I really like this figure from a paper by Alex Kendall and Yaron Gal in segmentation on the road. So this is a little bit hard to see, but there's a car on the road, so it's dash cam footage, and it's performing segmentation. So what's a car, what's a tree, what's road, what's the footpath. And what we can see is the uncertainty in each of those predictions. So a prediction is a color for these, which gives it a label of what it is. And so what we can see is that we have aleatoric uncertainty here and epistemic uncertainty here. So aleatoric is inherent in the data. So that means, so for example, it's usually on the edges because that pixel may or may not be classified as a car, depending on who's labeling it. There's no right answer. Same thing with like the leaves of the trees. It's like, does that belong to the sky? Does that belong to the tree? So you can't reduce that error by having more data because there's just that ambiguity. Then there's epistemic uncertainty where there isn't enough knowledge of data in the system. So that is related to how much training data you have, and the more the data you have, the more certainty you get. So here you can see examples. So here, it's all very gray. Is that road? Is it the footpath? And so if we get more data, the model hopefully should be able to model that better. So how do we go about quantifying uncertainty of a deep learning model? So perhaps some of you have heard of a technique for regularizing models called dropout. So in dropout, what happens is that rather than having a fully connected network, you randomly switch off neurons at each training step. So here's an example of some random switching off of the connections between the neurons. And the idea is that the model should hopefully learn a more robust representation because each neuron must learn independently of the others. The idea behind Monte Carlo dropout, or MC dropout, is to also apply dropout at test time. What that means is instead of getting a single prediction on the output of your neural network, you're now getting a distribution of predictions. So like every time you predict, it's going to be slightly different depending on the setting of these connections between the neurons. And what that means is now that we have a distribution, we can apply Bayesian statistics and quantify the uncertainty of this distribution. So by performing repeated iterations and analyzing the distribution on the output, we can determine each prediction's uncertainty. And we use a measure called the predictive entropy. So from some of your perhaps computer science courses, if you've done them, or perhaps some of the stats courses, entropy is just calculated as follows. So here's an intuitive example using the MNIST dataset, which is a dataset of digits from 0 to 9. So it's just grayscale images. Here they're represented using a different color map just for visualization purposes. And we can look at the predictions here. So we have the digits 0 through to 9. And the ground truth will have a 1 for the 7 and 0 for everything else. When you run a normal model, a deep learning model, you get values here, which are the softmax values. So they sum to 1, and you get some distribution. Get some values across there. If you run Monte Carlo dropout, you actually get a distribution, and then we can plot the mean and variance. So here we can see a little bit clearer here because there's more variance here. So that's in the output predictions. What we can see is that for some, it's not very clear what the digit is. So in fact, if we look at this digit, I believe it's a 5. So the ground truth here, yes, so it's a 5. The neural network model actually has a lot of uncertainty. So we can see that it's actually predicting that to be, I think, a 2, maybe a 4, maybe a 5, maybe a 6. I think it kind of looks like a 6, but it's really uncertain. You can see that with the uncertainty. And here's a lot of examples that show that high uncertainty. So here's a 4, a 5, and a 2. But you can see in terms of what the neural network thinks it is, we have a lot of uncertainty, which is represented by that variance. So what we can do is calculate the entropy of these distributions to give it an estimate of how certain the model is. So we can apply this on, for example, the chest X-ray classification dataset and model, and estimate the certainty of its predictions. Then what we can do is for the whole test set, we can look at that value that represents the certainty of each prediction and compare what it is for when it's correct. So when the prediction is correct versus when it was incorrect. So the green distribution here represents all of the image samples in the test dataset that were correctly classified by our model, and the red ones were all the ones that were incorrectly classified by our model. On the x-axis, we have how certain the model is. So higher certainty on the left and higher uncertainty on the right. Now, one thing we can do is observe the overlap between these distributions to give an indication of how well our model is performing. So what's the hope? We want the green distribution, so that when you're correct, to be certain. So we want it to be to the left. For uncertain predictions, we want them to appear on the right, so that we want them to be uncertain. We want our model to say, I'm actually not sure, and it got it wrong. What we can see is across the full data set, there's actually very high overlap. For COVID, also very high overlap. For the normal scans, it's slightly better. And then for pneumonia, turns out it's actually really good at classifying it. So it's more accurate, but not only more accurate, the uncertainty quantification for the ones it got wrong, turns out it actually knew that it was wrong. It had very low certainty for those examples. So it's another way we can actually inspect our models. So we can use those explainability techniques, and we can look at the uncertainty of the predictions as well. So some of the challenges are that, as I mentioned, accuracy alone is not a good metric for understanding performance. We saw that already. We got nearly perfect accuracy, but in reality, the model is using the wrong information, and that means it won't generalize to new data. If you have a new example, yes, it might be 93% on the test set, but you apply this in reality, and you're going to get a wrong prediction. So explainability and uncertainty quantification helps in visualizing and understanding the models as well as the data. To overcome some of those challenges, what we really need is well-curated data sets. So you would have seen perhaps with large language models, ChatGPT, that's trained on the world's knowledge of language. And to get those models better, a big thing is actually the data itself. So sometimes the model is only as good as the data that is fed into it. Garbage in, garbage out. But a big challenge is that we actually lack labeled data in a lot of domains. And that results in the models being overfit to the data that exists. And also we saw that the source of the data, as well as any biases in the collection, for example, having children only in a certain data set, can cause incorrect information to be learned. So one technique, so it doesn't necessarily solve all the challenges, but one of them is a technique called domain adaptation. So in some domains, labeled data can be abundant. So this here is now in a different domain. So one domain I work in, which is electromagnetic imaging. So it's using electromagnetic sensors, which are antennas, and trying to predict and visualize the brain. So produce an image of the brain using antennas, basically. What we can see is that these distributions differ. But before that, real data is actually really expensive and time-consuming to collect. As an example, a clinical trial costs millions of dollars to run, and after perhaps a year, you might get 60 patients which have the pathology of interest. If you compare that to simulation, you have full control over the data, so you can make anything that you want, and it comes with the labels because you're designing it. So that means that it can be abundant and it provides the labels. However, in different domains and different data sets, as we saw before, the distribution of the data may differ. So here is an example of real data. This is in linear scale, and here we have synthetic data. What we can see is that these signals actually differ quite significantly. So if you were to train a model on the data that's abundant and then try to apply it to real data, your model's not going to work at all. So one technique you can actually do is something called domain adaptation, where you adapt a model from one domain to another. So what we can do is one type of domain adaptation technique called a domain adversarial neural network, very similar to GANs if you've heard of them, so generative adversarial networks. And what it allows the model to do is learn domain agnostic features. So here's an example where you might have some target domain. Here, this is electromagnetic imaging in the lab. So this is real data from a real system compared to data that was collected in simulation. In simulation, we can control everything. So it's much easier to change the brain. Here, it's very difficult to insert a different brain and know what its parameters were. The way that you actually do this, Dan, is you have a neural network. So if you look at the green and the blue parts, it can be any network. So it could be a convolutional neural network. It could be a fully connected network. So basically, there's a feature extraction component, and then the last part, which does the classification. So that's called the label predictor. So that's just standard neural network. What you do, though, is you add this extra part, which predicts the domain label. So in this case, that would be, did it come from the source data, which is synthetic data, or did it come from this target data, which is the real domain? And so that's just a 0, 1 label, depending on where that data came from. And what we do is we actually train 2 different loss functions. So one is related to the normal class prediction, and the other one is predicting the domain. And now instead of making it better at predicting the domain, we do this thing called a gradient reversal layer, which actually makes the model worse. So what that means is we're trying to confuse the model so that it can't distinguish features from simulation or lab data. And so that's the trick. So relatively simple, and the only thing is the sensitivity of the model. Adversarial networks are always quite challenging to train. But based off this, what that means is now, eventually, once this finishes training, you'll be able to predict the label. So whether it's, let's say, an unhealthy brain or a healthy brain or whatever your classification task is, but you'll now be learning domain agnostic features. So it'll actually be able to utilize simulation data to run models on real data. So that allows you to use domains where data is abundant and then apply those models in new domains. So another important thing to consider in model deployability is the fact that currently everyone's competing about getting the best performance, so the best accuracy. And what's actually happening is we're pushing the model sizes to the limits of modern hardware. There was a video that went around a couple of days ago from Fei Li, very famous computer vision researcher, talking about how her lab in Stanford can't compete with industry because they only have 64 A100 GPUs. So if you think of massive companies like OpenAI, Google, Microsoft, it's huge. Like if you look at the amount of money they're spending on computation, I think it's better not to look at it. So the challenge is, in reality, not everyone has access to that hardware. So what we need is to actually be able to transfer these massive high-performing models to something that we can actually deploy and run on hardware that's accessible. So some of the stats is that ResNet 15 MobileNet are actually the most popular models on TensorFlow Hub download statistics. So the smaller models are actually downloaded much more than the larger models. That means that consumers, researchers, people who are training deep learning models, so people like you or I, we're actually using these smaller models a lot more commonly than we are the massive models. And there's that trend towards moving towards the source. So when you're running these models, you might not always want to run on the cloud, or you might not have access to a server. For example, if you're running some of these models in a hospital, you might not actually be allowed to transfer the data elsewhere, and you might need to run it on what's called edge hardware, so hardware that's small and at the source. So what we need to do is actually compress the model, and there's several techniques that we can use to do that. So just some of them are knowledge distillation, which is a training technique, which is hardware agnostic, pruning, where you prune or chop off some of the components of a neural network, quantization, where you reduce the precision of the numbers that you're using in training. So you may have heard of FP16, FP8. To the extreme, you can use just a single bit. And there's also another technique called low-rank factorization. So I'm not going to go into the details there. It's a little bit more technical and less kind of showy, but happy to talk about that after as well. So to summarize, deep learning models have achieved unprecedented performance in a range of applications. So we saw that in medical imaging, especially in health, that there's that trend towards AI-based models beating experts. However, relying on accuracy metrics alone is deceptive. There can be issues with the data or the training that can result in serious consequences when applying these models in practice. In fact, you might get completely wrong outputs when the distribution changes, or you just apply it in practice. So what we need to really do is actually make models more robust, reliable, and explainable through some of those techniques that I described. So explainable AI, uncertainty quantification, and then some of those techniques such as domain adaptation. Another thing to consider as well is that we need to consider also beyond just explainability. So when getting things approved, especially in the medical domain, there's the FDA, the TGA, the European equivalent as well. So there's a thing called reviewability. And so that is about exposing the decision-making process. So not just the accuracy metrics, not just the explainability, but describing the process that was gone through in terms of developing a system. So every decision that was made in developing the system, from the data that was used to train and test the systems, to the processes themselves as well. And the other things that are important are the fairness, the effects, and lawfulness of the automated decisions in practice. There are still a number of open challenges as well. So combining artificial intelligence and human decision-making is still a very active challenge. So we need some form of language to bridge between the machine language and human language. So one area of that is around concepts. So rather than those features which we saw weren't super interpretable, we want to move towards concepts that actually overlap between humans and machines. Also, there's actually a huge challenge with over-reliance on AI. So if we use the example of dermatology, they've done a study where they actually produced an AI model that was giving purposely wrong answers, and the less experienced dermatologists were relying on that, and they doubted their own judgment and went with the AI model, which was incorrect. And so we have to be very careful about over-reliance on AI as well. So when we develop these systems that need to interact with humans, we need to actually consider those human factors of how to actually get better decisions, especially when AI or humans independently might not be 100%. Also, there are challenges in applying a lot of these techniques to new domains. I gave a very high-level example of some of the work we've done in electromagnetic imaging. So that is working on signals, so time domain signals or frequency domain signals. So things that work really well in images don't actually directly translate into that domain. So how to actually get these state-of-the-art models to work in a new domain is really challenging, especially when I mentioned the amount of data. We don't have a million labeled images called ImageNet in electromagnetic imaging. So we need to develop new techniques to transfer to that new domain. Also, it'd be nice to be able to understand the effect of model compression. So when we're actually applying these models in practice, we can't use these massive models. So what is that interaction between performance, compressibility, and explainability? And I want to conclude with, if you're interested in working on any of these challenges, I'm interested in thesis supervision and also hiring PhD students. So please contact me. My email address is there. So thanks, everyone. I'd like to open the floor to any questions. Yeah, so the question was, are we looking at the live collection of that and of electromagnetic imaging data, and are there challenges in the hardware as well? Is that what you're saying?
Pretty much, yeah.
Yes. So I'm very lucky to be working with the microwave imaging group here at UQ, as well as a company that's spun off from UQ. And yes, we do have control over the hardware. When you're working in software, it's always a hardware issue. From the hardware, it's always, nope, you should solve this in software. But yes, there's a lot of challenges. They're also being solved independently by the company, but yes, all the way from sampling, how do we actually sample it faster, get real time, how do we make the algorithms better, faster? So looking at all those different aspects.
Is there much, sorry, I just have a follow-up on that. Is there much in the way of interference on the hardware side to
Yeah, so that was a question. Is there much interference from the hardware side? Yes. So heaps. If you think of antennas, so I'm not sure how many people still use real TV with antennas. So probably most of it's from the internet. But I've got a really dodgy antenna at my house that some channels just don't work. And like if you walk in front of the antenna, the signal just doesn't work. So that's kind of the antenna, that's the interference of your body against that. So we have so much interference. If you think of, let's say, healthy human trials, people are very cooperative, they can stay still. For clinical patients, they might not be able to stay still, so you get those issues. Also, the hardware. So, in simulation, you can assume you've got like perfect magnetic absorbers and electric absorbers. In reality, we can design ones that do a pretty good job, but you always will have that little bit of interference. And there's a noise floor as well. So even though we have state-of-the-art equipment, you still have that noise, which is more than what you have in simulation. So there are a lot of interference sources, but they are also being managed in various ways with hardware and software.
I found it quite interesting when you're talking about the domain consideration of the DAN technique, that you mentioned that the models tend to get more inaccurate once you do that, which I guess makes sense because you're removing some of the concepts or the techniques it was using to explain certain concepts. How inaccurate has it made some of the models before and after, just in your...
Is that with this slide?
Yeah.
So the question was around when you apply this domain adaptation, you actually sometimes decrease the performance of the model. It depends on how much data you have. In almost every problem, the more data, the real data you have, the better. So it's a little bit of trade-off, but you can actually get good enough performance for the task by doing this technique. So it does degrade performance a little bit, but it is still at a level that you can utilize it.
Yeah, I imagine it's more useful predictions because it's not predicting.
Exactly. Exactly. So it actually improves performance compared to just using the target domain, because the target domain does not have enough examples. Like you might have on the order of 100, but really for deep learning you need thousands of examples if you're not able to pre-train it with image-based models like ImageNet. So you don't have that, unfortunately, in electromagnetic imaging.
Statistically, so there's a median mode, at median. What usually performs best? I'm just looking at it from a TensorFlow way. Have you seen what statistical measure actually performs best?
Okay, so the question was around, you can use the mean, median, and mode for prediction. Which one works best? So I assume you're talking about ensemble-based methods. So I think that the mathematical derivations for uncertainty quantification are around the mean, because you can then average out the noise. And so I'd say the mean in that case, but there are various different types of ensembling that you can actually use different techniques. So I think basically you have to consider it empirically and see what works. Yeah.
I might have misunderstood, but I think at one point you said you could scale, was it the final layer down to a bit size of 1? Or?
Yes, yes.
How does that work?
So I had a point around model compression. There's a lab in, I think it's MIT, that does a microprocessor-based neural nets. So they'd go to the extreme where you have like a single bit, but it's not just a single bit on its own. So it's not literally you feed this in and like either triggers or it doesn't, like a light or something. It's like the light is on. But there's, it's composed of many different neurons. So like it's effectively triggering on something. And so you get like that single precision. That is literally the extreme, and the accuracy that you get is not great. If anyone's done any Arduino, like TinyML stuff, the demos, promise so much. Like, they've got that keyword detection. You watch the demos, it works really well. Then you try it yourself, and it's like, it's not picking up my Australian accent. And so, yeah, it doesn't work as well in practice. So TinyML is an example where they actually do all that quantization to really small precision. So it really depends on the application, but you are degrading performance significantly, but you can, with the composition of neurons, get something that is publishable and has nice demos.
That's cool.
Yeah. Great. I guess if anyone else has any further questions, I'm happy to answer offline as well.
Okay, so yeah, thanks for coming along and presenting. I'll end this now. But yeah, thanks for coming along. It was very insightful. I'm sure everyone got a good bit out of it.